All right. Welcome everyone to the AI for Seals final presentations. Today we have three teams who will be presenting for us who have worked very hard over the last 10 weeks. But before we get into the challenge, I really want to thank the challenge partners for the AI for Seals challenge. First of all, of course, Colgate University, and special thanks to Krista and Ahmed for working with us over the last 10 weeks on this amazing project. Also, special thanks to Atsala AI Consulting and Engineering for their expertise and their help throughout the challenge, and Huawei for being one of the main sponsors in our AI for Wildlife lab. Today, I will do the challenge introduction, then we will go into face detection team, which will be presented by Mohammed Hassan. After that, you will hear from the face recognition team, from Roshan, Victor, Nicholas, and Jaka. And finally, you will hear from the machine learning application team, which will be presented by Daniel and Graham. And as some closing words, me and Krista will do a short word. So for the people who are new here with us, we are FruitPunchAI. We are the global AI for good community. And we started this community because we believe that to solve humanity's greatest challenges, we need to educate AI engineers at scale and with the ethical and sustainable mindset. So how do we educate AI engineers at scale? We do this by challenge-based learning. We organize challenges related to all the sustainable development goals, and we do this all over the world. For this challenge, we teamed up with Colgate University and their researchers to tackle a problem with seals and face recognition. Over the last 10 weeks, we worked with 3 teams and over 35 AI engineers with a combined effort of more than 2,800 hours on this project. And we aimed to increase the accuracy and robustness of SealNet, as well as the automated facial recognition technology for identification of seals. So we set out with a large data set of identified seal faces, and we build an application where we can create or where we can upload data sets of seals, where we can detect their faces, recognize the individuals in the pictures, and then host this in a web app where we can, where multiple researchers all over the world can actually use this. So I don't want to take up too much of the time, since most of the interesting information will be coming from our teams. So I would like to give the face detection team the floor right now.
Yeah, hello everyone. So we are from the face detection team, team 1. And this is the agenda for today. So first I'm going to introduce the team, then what were the goals and solution, direction and struggles that we have faced. Then I'll take you through some results and demos on which we have worked. And finally, I'll discuss the lessons that we have learned. So this is the team, which team 1, which we're working for the face detection. And most of these who are listed here were not very active during the this project, but many of us have contributed. And the goal, our goal was to develop a model to detect the seal faces. And the goal which were given to us is to improve the accuracy using the modern framework and augment some data set, like experimenting with the half seal faces and to find out whether we need to align the faces, etc., as well as to enrich the data set is by labeling more faces and finding more data set for the different species and labeling them also. So, however, while working on this project, we have decided a few tasks that we should not follow. So the first thing that we haven't did is experimented with the half faces. And we did only focused on the full seal faces, because first we wanted to try how does a new model that we are going to build performs on the full seal faces. So we have skipped this part, and we have also skipped the faces alignment. And we have used the modern YOLO 8 framework to improve the accuracy. And we have seen that the YOLO 8 framework has given us a very good accuracy. And then we did also tried some other models also, like YOLO 5 and others, and even YOLO 7. And we have compared the accuracy with the YOLO 8 model. So uh, the two of the models has given us promising result, and those are YOLO 8 and YOLO 5. So we have compared the accuracy of these two models. So we labeled more faces, and then we have also applied some augmentation using the RoboFlow platform, because first we did try to train a model without augmentation. So in that we did not achieve high accuracy. So we tried with the augmentation, and in that we received good accuracy. So while training the model, the accuracy, so we did consider the two models, although we tried different other models also, but due to the high accuracy, we considered only these two models for comparison. And you can see that the YOLO version 8 model performs uh, very well as compared to the YOLO version 5 model. And these were the training matrices. And here are comparison of some of the images uh, in the YOLO version 8 as well as the YOLO version 5. So here you can see that the in the YOLO version 8 model, we received good accuracy, and at some part the YOLO 8 model is also uh, able to identify half seal faces. And here it does not identify because we skipped labeling these kind of seal faces, and hence it is not detected by the model. And here are some more results. These are the images which contain uh, more instances of seals, and we can see that the model with the YOLO version trained with the YOLO version 8 is able to detect all the seal faces which we have labeled. So the lessons that we have learned with this project is some of our team members have learned how to use the RoboFlow as well as weights and bias. And we did also learn that the whenever we are doing this kind of project, so it's always good to start earlier and focus on the problem that we need to solve. And we did also learn that if we could use semi-supervised labeling, so we can get more promising results. So these were some of the lessons that we have learned during the course of this challenge. So thank you. This is all from our team side, and now I'm open for the questions.
So around each box of the seal face, you've got numbers. Is that the accuracy of the YOLO 8? What does that represent?
It's the confidence score, how confident the model is detecting. Yeah.
And so most were around above 85 to 90. Some were 45.
Yeah, above, yes.
That's a confidence. Yep. Mm-hmm.
Yes.
So what confidence would you be confident in?
So you can see that mostly the confidence score is higher in the YOLO 8 model that we trained.
One useful thing about the confidence score is you can set a threshold. So for example, that could be kind of like a configuration item where, you know, that you say the confidence level must be over, let's say 0.75. Otherwise, you kind of ignore the detection. And so the practitioners who are using the model can therefore control. It gives them a degree of freedom to kind of like what you're asking, like what's the best confidence score. So it's sort of hard to tell until you start using it what that threshold should be set to.
But then we could set a threshold, and that way we're just getting high confident data. Yeah, thanks. Mm-hmm.
Yeah, you don't have to retrain the model. So it's like a way to do the fine tuning of how you use the model.
Great, thank you.
Yeah. So like for detecting, while we have applied the model on the test set, so for detecting the seal faces, I applied the confidence threshold of around 40.
Cool. Yeah, so we're halfway through, so I really want to head into the next presentation. Now we have coming up a whole team of presenters for the face recognition team. We have Roshan, Victor, Nicolas, and Jaka. So whoever wants to kick it off, take it away.
Okay, I'm Roshan from Team 2. So basically, we worked on face recognition of the seals. Yeah, so this is our team. Most of us were coders, some of them were managing the tickets. Yeah, so this is a bunch of people who really worked hard for 10 weeks, and we're going to present our result. So the goal of the project was something like this. The main goal was to retrieve the most similar seal images given a probe seal image. So in not just predicting the image class, but we wanted to have a mechanism where in addition to providing the prediction scores or the similarity scores, there should be a provision for the end users to visually check the images, predicted images. So these were our main goals. And our approach was something like this. We started with the very simple models, which we call as a baseline models. And then we moved towards the more complex ones like EfficientNet B0, Siamese network with the ResNet 50 as the backbone, VG16 with the cosine similarities. So the reason for choosing EfficientNet is, as you can see in some of the graphs here, they perform really well for the image classification activities, and that's why ImageNet B0 was chosen for our. Coming to the experimental process, we combined dataset 2020 and 2021 for the simple model, that is HOG plus SGD and image area plus SVM. We had 9 different set of experiments conducted for different image sizes, like 112 cross 112, 120, 200. And the minimum number of files that were chosen and the maximum number of files that were chosen were 5 to 10, 6 to 10, and 7 to 10 in most of the cases. So these were different kind of experiments that we did with our models. So of course, I'm not going to present all the results here. I'm going to choose some of the best results for the simple models here. So when we use HOG, that is histogram of oriented gradient descents with the simple gradient descent model, and choosing minimum file of 7 and maximum file of 10, these were the accuracy that we got. You can see that the accuracy is pretty good. Verdict. So HOG SGD plus is better compared to the image vector SVM model. We can still increase the accuracy of the model. Yes, we can increase. The grid search is one method to do that. We already have the code available. There is already the code available. Only thing is it takes a bit more time for executing, because there is a lot of parameters that you have to sweep. This is how the result looks like. You give the probe image, it gives you the prediction accuracy, and it gives you also the different labels, the top 5 results. Same case with the image vector. It gives you the accuracy of each labels and gives you the top 5 values here. This is how the interface looks like for the basic model. You can specify where your directory is. You can specify the minimum and maximum files that you can use. You can resize the image to whatever you want. You have for now we have only the default version available. It gives you the raw classified samples, classification accuracy, and this is how you can do the inference. You can check any one of these images, open it, and then it gives you the prediction accuracy. It says, okay, I can correctly predict that it is seal with the label called Cooper, and these are the prediction accuracy, and these are some of the images that you can manually check for. So basically, this is what we have done for basic simple base model. Going back to the more complex models, I hand over the presentation to Victor and Nicolas.
So yeah, hey everyone. As Roshan introduces, thanks a lot. Victor and I, we're going to talk a bit about FruitPunchAI, which I believe is the best performing model we achieved for the face recognition. So I'm going to try to keep it in simple terms for all of you that are not really familiar with all the ML technicalities. And please feel free to ask questions if you need so. So basically, we attempted to use deep learning, which it has been widely used as an ML tool, and usually is the one that presents these results. And the thing with deep learning is that deep learning architectures tend to be very, very complex. And when these architectures are very complex, when you have little data, you tend to overfit to your data, right? So often one of the techniques that is very useful to use is this thing called transfer learning. That means that you take a model that was trained with a very big data set for a certain task. In this case, we choose FruitPunchAI, that was trained with a very big data set on images. It was trained to classify with a huge data set with thousands of classes. And then what we do is that we take that learning weights like that, that knowledge that the model did, and we just freeze that knowledge, and then kind of like append our very tiny classifier in the end. And what we do is, thanks to all that learning of the big model, we just use it to kind of like fine tune this small classifier. So this technique is usually called transfer learning, and that's basically what we attempt to, because in particular, FruitPunchAI has been widely used for this task. Apart from that, we added on some more fancy features, such as some augmentation pipeline that applies augmentations on the fly while training. Those includes random rotations, translations, flips, and different contrast levels. And that was all for training, right? So once we train the model for 20 epochs, we basically, what we do is we drop the last layer, and what we end up is with a network that once you put an image of a seal in the input, outputs an embedding of the seal that represents in a complex way the seal, right? So what we do is that we go through the whole data set, and when we obtain all of the embeddings, and then we just compare them through a type of similarity function that is called cosine similarity. And this is a very, could you just go to the next slide, please, Roshan? That's a very simple way of how things work with our model. Basically, we will have this probe sample following the same fashion as SealNet, which is marked as red. And then on the upper row in green, you can see the samples that belong to the same class, that is the images that belong to, in this case, I think is compass, this seal. And then in the lower row, the five seals in blue are the highest similarity results. Well, as you can see, well, in this picture, it was too small, so I kind of like, I didn't mind covering with the square, but it was pretty accurate on finding in this particular seal. So if you could move to the next slide, please, Roshan. Thank you. So what we did is that we tackled the evaluation of SealNet in two ways. First, we wanted to do a fair comparison with the results produced in SealNet. And at the same time, we came up with another way of testing the generalization of our model. That means we wanted to evaluate how good it was at generalizing at seals that the model had never seen before. So for the first comparison, basically we did the same procedure as done in SealNet. We only selected seals with 5 or more samples, and then we applied 5-fold cross-validation during training. So after that, we ended up with 74 seals, basically. If you move to the next slide, please, Roshan. Yeah, so basically, these are comparison between our results and SealNet results. And on the right, we have our results in different metrics, in accuracy, precision, recall, and F1 score. So basically, as it can be seen, our model is slightly lower than what we achieved in SealNet by 2%, more or less. It is remarkable that this is a very simple, straightforward way of training our model, and we spent in the end more like 2 weeks on FruitPunchAI. So more work could be done in many aspects to keep improving this model, which make us think that actually this is quite it is quite powerful, and it could lead to even better results than SealNet. Regarding the evaluation of the generalization, what we did is that, if you change the slide, please, Roshan. Yeah, what we did is that we tested on all the seals that the model had never seen before. Those are the seals that had between 1 and 4 samples. So if you can see, as you can see, the results are slightly worse, quite worse the top 1, but slightly on the top 5. And this implies that there is a slightly overfitting in our model, which we argue that belongs to the fact that the seals have few samples. That's a fact. And also the samples between, it's like in each seal, are very similar to each other. So that, like, the little variability between images, that doesn't help. So yeah, I mean, more work is needed in this case, I guess. If you could move to the next one. Thank you. Regarding the next evaluation that we did, is that we decided to join the data set that we had in 2020 plus the data set on 2021, and we did the exactly same 2 evaluations. So if you move forward, Roshan, we found out that the performance decays with the number of seals detected. So before we were trying to classify 74 seals, while in this one we're trying to classify 110, which is almost half of the previous data sets. And still we can see that FruitPunchAI is quite robust, although you can tell that there's a decay on the performance. But more work should be done to find a good compromise between the number of seals that the model can learn while performing in a specific threshold limited by you or biologists. And yeah, the next slide, as Roshan did very smartly, is that is the same as before, the generalization test. And as we can see, there is also a slightly worse performance, but in this case, it's even lower than before. And yeah, same conclusions as before, basically. And now I'm gonna give the floor to my mate. I forgot your name. Sorry.
Victor, yeah.
Victor. Sorry, mate.
No worries. Yeah, thanks a lot. So here I'll just spend a few minutes talk about some maybe additions to the FruitPunchAI model that we tried, but also that can be used for any model architecture, which I think would be nice to have. So I'll talk about explainable AI. So basically the concept of model explainability allows us to understand why our model predicts the way that it does. And this can be useful for several things. So in our specific case, it can help us understand why it matches several seals, like that they're together or the same seal, and which facial features it uses for specific scenarios, but also in general, like by looking at doing a vision analysis of this, we can theoretically see that, for instance, the model has learned more that the eyes differentiate the seals, or the mouth with the position, etc. And also what's important is to see that, because as Nicholas mentioned, that some of these models may overfit, and sometimes to see that the model doesn't look at any additional information beyond the seal. So for instance, I'll show you in a few seconds an example where, because all of the training images of the seal are in one position and have like one patch of background, then the model might use that patch of background to predict that it's that seal without even looking at the entire face. So how it works, in this case, we'll be working on the SHAP approach, so which is sharply additive explanations. And as you can see here on the right image, basically the goal is to give an input image, and based on the model predictions, it tries to specify which pixels or which parts of the image are more important to the prediction, either positively or negatively. So in this image, we can see, for instance, the meerkat is the clearest example that the model has very high activations towards the eyes, so that's why it predicts that it's a meerkat. While on the other side, if we look at a mongoose, which is relatively similar to a meerkat, at least visually, it's the second most similar animal, but it has negative, so you can see small blue activations near the eyes, which basically means that it's not mongoose. So if you can turn the next slide. So this is what we did also in our model. So here you can see that the resolution is much more coarser. This is mostly due to time constraints. So this is done in the last few weeks, and there are some limitations in the aspect when you have to generate this. But since the code is available, I think we'll be able to generate even nicer ones. So here you can see, for instance, on the left side, you have the probe image, as we call it previously, and on the right side we can have the top 5 predicted classes, as well as the positive and negative activations. So first of all, you can see that in this case, the first column after the probe image is the one with the highest similarity. So our model performs pretty well, but we can also look at it, for instance, for bonsai, the prediction is highest because of his right eye area. In Ash, it is highest because of the top right pixel of the image, which doesn't make the most sense. While in Shamu, we get the best results out of that. It is basically because of the eye and the mouth area, which is what we expect. And on the other side, we can also get some why, for instance, the second example had lower values. So for instance, if we look at Shamu again, then Wonder is the second highest image, and I didn't upload the image of Wonder here as well, but we can, if you check in the dataset, it's very similar visually to Shamu, but we can see that near the right eye, there's a small negative correlation, which leads the model to see that this is Shamu instead of Wonder. And this is information that we would like to have also, for instance, when doing basically when looking at these top 5 visualizations in inference, to see not just by yourself whether the probe image matches some of these 5 images, but also maybe use some of these aspects to sort of see what the model focuses on, and also maybe what you should focus on as well. Next slide, please. Here we have some of the same results with a slightly higher resolution, but only for one specific image. So in this case, we take Armani as the probe, and we could look at the 4 different images of Armani. And basically, we can see that, again, the model predicts pretty well, and some of the images that are the second highest, like bonsai, chance, and flora, are seen on the right-hand side. So here we can see that most of the predictions are because of the eyes. So especially in the second, third, and fourth image. But in the first row, we can see that, for instance, there is one very high activation, which is on the top right corner, which might be not as legit in this case, because it's mostly background, basically, which repeats in the several images of Armani. Yeah, that's all from me. So I think Jack is next.
Let me change it. Yeah. Floor is yours, Yaka.
Thank you. So I think we're a bit over time, so I'm going to try to make this a bit quick. But basically, while we've been experimenting with different models, we've also given a try to Siamese networks, which are an interesting type of network for finding similar images, which is exactly what we're trying to solve. And the idea here is that instead of learning what different classes look like, we're basically learning directly the embeddings of images, and we try to output a dissimilarity or similarity score for those embeddings. And the way they work is that they have 2 sub-networks which are identical, and they share the parameters and the learning process. And after we compute the embeddings with them, we try to compute the similarity of images. And for that learning process, we use different kind of loss. We can either use a contrastive loss or a triplet loss. In our case, we experimented with contrastive loss, and the contrastive loss's job is basically to, during training, present 2 either similar cases or 2 dissimilar cases, and then we try to maximize the closeness of similar classes, and then to minimize the distance between similar classes and maximize the distance between dissimilar classes. And the advantages of such networks are that they need way less training samples per class, and hence we can get rid of the restriction of using only the seals for which we have 5+ images, which is quite nice. And they're better at learning semantic similarity of classes as opposed to just focusing on particular features. But they also have some disadvantages, and one of them is, sadly, that they don't output probabilities or confidences, so it's a bit harder to evaluate using traditional metrics. So you can't really say how accurate they are, but you have to use other methods. And they also have longer training times, and for some cases, you can even go up to like 150 to 200 epochs, which is potentially 4 times as much as classification. And because we're using contrastive loss and you're presenting 2 similar or 2 dissimilar cases, if you have errors in your labels, this really disrupts the learning process, which is quite a tough one. Yeah, Roshan, you can move to the next one. And for Siamese networks, we basically prepared a simple pipeline so that it's easy to train these models. We have it in Python, so if anyone wants to play around, it's quite easy now to train these models with the data sets that have already been mentioned. And we have used this to train a bunch of Siamese networks, basically following the experiments we've done in the EfficientNet series. So we tried different stuff with different image resolutions, different similarities, and so on. And we found here that basically for Siamese networks right now, the best configuration is a RigNet 16, a really nice architecture. I recommend it to everyone, on image sizes of 224 by 224. And this was trained for 51 epochs, which is, in my opinion, not really enough. So this would need to be extended to get really something that we can rely on. And Roshan, if you move on, we can see here some nice visual results, where we basically used 040 carry as a probe image, and the result is to get 2 carries and 1 Dakota, which actually looks a bit like carry. So I'm not really sure if it's the same or not. And then we get a carry again. And then, yeah, you can move on. And then we have a similar example for July 12th, Bastin's Ledge 38 seal. And you can see here that despite the next image being quite dark, it finds a nice match between the two. And the third one, and then we get two shamus. Probably that's because also of the degraded image quality that we use per probe, and this I think is not visible. But as you can see on the numbers above, the distance is much larger than the closest match, which is 13. And if you actually match the same image, the distance then really drops. So these distances are actually quite a nice indicator here. And it is distance, as I said, so it's not 100% similarity or 90% similarity, but it's actually distance from one to the other image in the Euclidean space. So based on these visual results, we can definitely say that CME's networks do work for this case, and they are something that you may want to try using in the future, but they did require a lot more work than efficient net, which makes it a more suitable solution for the scope of the challenge.
Yeah, so sorry, the presentation got off automatically. I think we took more time than needed, but there was so much of work that we did, and just didn't want to lose anything in the presentation. So that will be all from team 2, face detection. If you have any questions, please fire away.
I had a question about efficient net. So it looks like you guys use B0. Did you try any of them? My understanding is that that's like the least powerful one. Did you try any of the larger efficient nets?
No,
Yeah.
so
Sorry,
maybe Nicholas. Yeah.
Yeah, I can take this. Yeah, thanks for the question. That's a good one, and indeed we tried. We did with efficient B2. For the people that don't know, efficient B0 can range from B0 to B7, and the larger it gets the number, the larger it gets the network. And the problem is that as soon as we start getting larger networks, we experience more overfitting quite quickly. So yeah, we ended up sticking to the smaller one, which in the end also makes sense regarding the resource usage. But yeah, if you end up with more data, then you can try with bigger ones. We thought with the combination of 2020 and 2021 data, we could maybe, but also it overfit. So yeah, we stick with B0 in the end.
All right, yeah, we're going well over time, so I want to head into the machine learning application team, and we have Daniel and Graham who will be presenting for us. Very curious to see what they have come up with for today.
Can you guys see my screen?
Yeah.
Yes.
Okay, great. Okay, so I'm Daniel Kritzinger, and I want to be presenting for the ML application team, as well as Graham Harris, but I'm going to start it off. So I want to try and be quick. So just to provide a bit of context, where this all started was that the aim of this whole thing was to create a non-invasive tool for tracking individual seals in ecological and behavioral studies. And essentially how to do this is obviously by identifying the faces. When you can identify the face, you can use that face and put it into the recognition algorithm and identify the seal. And then you could track these seals across different locations as you identify them. The core problem with this is, however, the fact that it's very difficult and time intensive to identify seals from images. And there's a lot of admin required in efficiently keeping track of all the associated research data, such as the image capture locations, the behavior notes, observation notes, all of this. So the original solution, SealNet version 1, which you guys can see here to the right-hand side, aimed at creating two applications or creating an application to help with this detection and recognition process and making it more automated with manual steps to kind of correct for issues with the models. And they managed to achieve that pretty well, and it works pretty well, as Amit and Krista have explained to us. However, there were a few deficiencies. Firstly, it's a relatively old tech stack. It was also desktop applications, which complicates the data sharing and collaboration process. It's two separate applications, and it's not very user-friendly for non-technical users. So that's where the ML application team comes in. And our aim was to try and rebuild these separate desktop applications into a single application aimed at improving the user experience and adding functionality for better data management. Initially, we had various discussions with Krista, and we tried to do some planning, and we got down to like the core features that we would need for a system like this, is we would have to be able to upload images of seals linked to specific locations and dates to create like an observation. We want to be able to add descriptive notes to these observation sets in order to note on important details of events, such as weather and so on, and how that affects, and obviously researchers could use that. We wanted to be able to, obviously the core of this, automatically detect all the seals in the observation set to assist in linking seals to observation locations in order to track seals. We wanted to be able to have the researcher verify the automated seal detection, and then at the end of all of this, if you have a proper pipeline that is able to identify and you verify the data, you want to be able to download all of this data and do further research on it, as well as be able to collaborate with other researchers. So just to be upfront, unfortunately, we did not achieve, we're not able to complete everything, but I'm going to be, me and Graham are going to be taking you through what we did achieve and how we achieved it. So yeah, just to get to the initial system and how we kind of planned it, is initially there were two important design considerations. Because we wanted the application, and after discussions with Krista, we realized that this app really has to be a collaborative app where you can work with other researchers and students and so on. We needed it to be a web application, which immediately makes it a bit more complicated. And also we needed it to be, and all the components that we built for it has to be open source. So for this, obviously those two design considerations played a big role in deciding on our tech stack and how we actually wanted to build this. And you can see to the right, this is basically the framework or the architecture that we work with. So you can see it consists of 4 components: our front end, our back end, the ML endpoints, and the databases. For the front end, we went with the Next.js front end framework, just because it's built on React, and React is a massive community and a lot of open source components. And hopefully, the hope was that this would allow us to be able to develop a lot quicker. For the databases, we needed to store 2 separate types of information: all the images, and then also the relational data, the text data. So images, we'd have to store the raw observation images that the researchers actually took. But then also in the process between the recognition and the identification and recognition steps, there's also a step where you actually have to crop out the seal's face and save that as well. So that also had to be saved as an image. And for this, we selected S3, AWS S3 to use. It's an industry standard. Colgate already had AWS access, so we thought this would be the perfect for blob storage. And then for the relational database, we went with Postgres just because it's also a very well-known database, and it's fully featured and it does everything that we want. And for the backend, we went with Fast API just because it's Python-based. A lot of the people that worked on this project had experience with Python, and me personally had experience with Python. So we decided to go with Fast API and SQL Alchemy for the object relational mapper. Something that I do have to note on here is that we specifically chose to make the ML endpoints their own components, just because we felt that we wanted to keep the backend as static as possible and only have like a set input output from the ML models, so that further development can be done on the models without affecting the core application. So if so those are essentially separate and also wrapped with Fast API endpoints. So just on how far we got with the backend, we really put in a lot of work into this, and we tried to get as far as possible, but there was just a lot to do. So what we managed to do was essentially create all the authentication routes and have authentication perfectly running, so you can log in, sign up, verify your email, refresh tokens, and or actually I didn't put it in. We can also reset your password. And then there was quite a few CRUD operations that had to be done. You have to be able to manage all the observation sets. You have to be able to manage all the seals, all the raw images, all the detection annotations, all the recognition annotations, and obviously users as well. So you can see there with the check marks how far we got. With the recognition annotations, we did actually get quite far on the back end, but I decided it wasn't completely done, so that's not completely finished. And for the users, you can see we have a few user routes. The only one that's missing here is being able to update certain details about a user. With regards to the ML endpoints, from the Flommers team, we actually got a YOLO V8 model. we wrapped that and we were able to test it out a bit. We used the YOLO V8 model and it worked perfectly. And that is actually integrated into the backend at the moment. But with the recognition model, we didn't get as far as actually having that completely wrapped and integrated into the backend. So that still has to be done. Yeah, this to the right is just the automatic documentation that Fast API creates for you when you build the backend. And yeah, so for the next part, I'm gonna give it over to Graham, so he can do a bit of a presentation about what we were able to finish on the front end.
Sure. Hi, everybody. I haven't been able to make these meetings for a long time, so I'm coming out from the shadows. Good to see everybody. Yeah, on the front-end side of things, I took on my artistic cap. The phrase I always say is that I will do front-end development if you put a gun to my head. So just with some caveats, it's a bit rough around the edges. But again, the choice of React, etc., was the hope that as we go forward, at the very least, anyone could pick up the mantle if we didn't get all the way to the end. So I think it's in a pretty good spot, and some things can be neatened up and made a little pretty. But this is where we started out. Back in the very beginning, I did a little Figma wireframe outline back when I was feeling high in spirits during the holidays and felt like I had a lot of free time. So it is very ambitious, and there was a lot that we thought we could try to get through. Obviously, not all of this was intended to be completed. For example, we definitely thought that the map interface was something like a pie in the sky shot and, you know, shoot for the moon and maybe you'll land amongst the trees kind of thing. But yeah, I've got to the next one, Dan. I can run you through how we got through things and what actually ended up working. So the main ideas really were, key thing is it should be easy to upload data. That was something that was quite a pain on the previous application. And web interfaces can do that quite easily for you these days. So just making sure that form is easy to interact with and very low in friction. If you could look back one, then yeah, there we go, sweet. Easy to visualize the observations and use as much people as possible, right? React open source libraries, just so we don't waste time moving around stuff that's already built. But yeah, on to the next slide. Something that I took as a bit of a segue was I thought it'd be quite cute to just use some image generation to give us a little logo. So there's a little SealNet logo. Krista did note, however, that Midjourney isn't aware that seals don't have feet. So it is half of the way there. It's a little anatomically incorrect, but it's quite nice. So that's our SealNet logo. I thought it was quite nice to keep my spirits high while I was deep in the CSS code. And it looks kind of cute, and we'll see if anyone wants to keep it around. But yeah, that was just a little brief aside of using AI in the design process. But onto the next slide, I can show you a bit more of what the website looks like. So the form is a little bit sparse, a little bit Spartan, but it does do what it needs to do very quickly. So we used AntDesign just to quickly throw things together, which gives you a modern interface very quickly. So you can do your date picking with a nice modern date picker and everything in details. The way we got to the ideas of what needs to be added to this form was just with an interview with Krista. And that drag and drop interface helps upload files, save them into local memory in SQLite, and then that can be synced up to S3, which is a fairly standard way of doing things for blob storage of images. Yeah, and again, the whole idea was that this is very easy to change if someone needs to change what that form upload looks like in the future. So it was just a quick outline of making sure we can create observation sets. So that's our main form of creating observation data sets, which, yeah, I think you've seen and interacted with on data team side. Those would be the huge files of things called like July 13th cliff site. This would be a way to just quickly upload those files and get them workable. Once those are uploaded, I think on the next slide, Dan, I created a nice little modern view of what those would look like. So it's just a gallery view of all the data sets, which you then can click on and interact with on the data that is contained within those observations. And again, I just chose a random image to be the cover image. That could be changed to like a gallery or something. Again, very artistic subjectivity. And as per usual, this is something that's using some pre-built components. But one thing I should note is that we were hoping to use Label Studio, which is a very big open source project that does a lot of the management of data and of labeling, so bounding boxes for face detection, etc., or just general object detection. But at present, I was actually in their Slack group for quite a while over these 10 weeks trying to work things out with them. It doesn't currently work with static site generators like Next.js, which is something that was a bit of a pain, and we'll talk about down the line. But onwards with life as we go. But this is eventually something that we did use. So this is a tool called React Image Annotate, and you can see the UI interfaces are a bit wonky in the top right, but it does work, which is nice at least. And it allows you to have a very easy way of working through annotation tasks by loading in a set of pre-loaded bounding boxes to JSON data. So for example, what the workflow would be perceived to be is You run this through the YOLO V8 model. You get a set of assumed bounding box models that can then be displayed onto the image automatically using this library. And then you get given an interface to drag around those boxes and then confirm whether it matches the categories that you want it to. This was quickly done with default categories, but it works really well. And I'm quite happy with that integration and how it works to provide that labeling interface for the users. Onto the next page, Dan. And then on the other side, on the seal recognition side, this is probably the roughest interface. But what I really wanted to do is just provide a nice view of what the probe could look like and what the next most recognized seals in the observation could look like. So in this case, I used Dagon and just gave a nice overview of something like the confidences that could be related to the Dagon images, which I think you saw presented in the previous presentation. You can kind of just apply that into the screen. Again, it works with nice JSON data, so it's more of just a screen that would take anything that that model gives us. And yeah, this one is probably the most rough around the edges, but I think you can get the idea of what we would show off here. Yeah, I think that's pretty much the main screens and stuff we got through. There's also the login flows and the profile page, but I didn't want to go through a full demo. We're already pretty much over time. But yeah, we integrated a lot with the backend. It's just making it nicer and really putting a lot more of the validation sides and integrating with ML models all the way through. But I think we're pretty happy with where we got. Yeah, and I want to thank everyone that came through to help out, Evan, Faith, and the rest across the community, pushing through the CSS pains. I really appreciate it. Yeah, I'm not sure if you want to go to the next slide, Dan. I think there's one thing, just a highlight of where things sit. So we're happy to upload image data. We can create new data sets, manage all the labeled data, do profile management for users, etc. The only main thing is, right, the ML inference is rough around the edges, and we didn't really do an image view around maps. There are some open source React libraries that we could use to just display lat long probes, which could be interesting if someone is curious about that. One thing I would really like to see as a future interaction is something like including the weights and biases training panel or something along those lines, just to allow people to retrain the interfaces as we go. I know that would be a big part of what we could do. And I think it's fairly easy to do that. And also maybe work back to get some stuff from Label Studio, because I think they provide a lot of useful stuff. But that's where the front end sits. And yeah, thanks everybody for your time. I think that's pretty much me. Thanks, Dan.
Thanks, Graham. Really appreciate it. So yeah, unfortunately, we didn't get everything done, and there were obviously some challenges. I think the main thing is that we were a relatively inexperienced web development team. This is the first time I've ever built a web apps backend, and I kind of just learned on the fly, so it was a bit of a process, but I really did enjoy it. I think the other thing was initially we had some troubles kind of identifying what tools to use, specifically with regards to our tech stack and the labeling. Like Graham mentioned, the data labeling tool was a bit difficult. This was quite a big component. We knew that wasn't something that we wanted to build ourselves, so we wanted to identify something that works properly, and Label Studio was going to be that. But yeah, we learned that wasn't, that just didn't work with what our system was at that point. And then I think, I don't know about the other teams, but for our team, definitely communication between the team due to like different time zone and personal commitments was a bit difficult, and we struggled with that a bit. Lessons learned from this whole process. Well, I learned a lot about web development, but basically building a web application in 10 weeks is difficult. And yeah, so that's basically the main takeaway. And I just want to kind of end off and say that, I'm very proud of what we actually got done, and I'm really appreciate all the team members actually stepping in and helping with the stuff that we were able to build. And just thank you to all of you guys.
And a small point on Scout's honor, both me and Dan are happy to still provide support to make sure that it's at least in a limping state, so we don't leave it dead. So this isn't just the end of this, and so hopefully it'll look great in the future. Yeah, there we go.
Yeah. Okay, so I'm going to stop sharing.
Really thank you guys. I know how hard you guys worked on it, and I'm really proud of how far you guys came. And indeed, what you say, Daniel, it's very difficult to put that much work into a 10-week project. Even harder maybe if everyone is also working full-time, part-time, besides working on this voluntary project. So yeah, my head's off to you guys for working so hard and getting so far. Nicolas has a question.
Yeah, it's more like a comment for both you, Daniel and Graham, and I guess you, the rest of the team. It seems really great what you did and what you achieved, and it seems very cohesive. So shout out to you, because it's not easy. I think all of us struggle with different schedules, and what you did, guys, seems really nice, really advanced. And as a further comment to go what Graham mentioned, I'm also available if you guys need to integrate the face recognition part on the application.
No, I also just wanted to comment that it's very impressive how far you got. Like, I've been in a lot of these software development projects. They take way longer with way more focused teams to get to the stage that you guys did, especially also based on the experience. So my hat's off as well. Like, congrats and thanks, guys. It's really impressive.
Yes, I do. I'll be really quick because I know everyone stayed late, but wow. Wow. This was really an incredible experience. So as I said earlier, at the beginning of the challenge, Ahmet and I were really humbled and honored that FruitPunch found us and wanted to create this challenge. So I did want to do a quick shout out to Tumi, Dorian, and Sako for your patience with us. But mostly I wanted to save the thanks for all the people on the screen and all that just amazing contributions you've made in the 10 weeks. And it's all volunteer, and we recognize that. So it's just sort of overwhelming. Sorry, but I couldn't think of how to thank you since I don't even know where you are, but I wanted to share something. I'm not quite sure how to do this. I'm going to try. Dorian, if I can't do it, are you seeing anything? Yes, starting to?
Yes, it's coming up.
Okay. And so then what do I do? If it's PowerPoint, I show it, or let me just see if this works. Sorry, I haven't used Google Meet.
Yeah, now it's working.
What do you see?
Almost. Yeah, if you hit present right now on the bottom right, I think it is in PowerPoint.
Okay. Where's the stupid present?
Yeah. No.
Oh, hold on. Okay, so I couldn't really think of how to thank you other than, and this is going to kill the face detection labeling people, but I might have to go back and label some of these seals with a different name. So are you seeing a seal right now?
Yes.
Yeah.
This is Daniel. Yeah. Thank you so much, Daniel. And then we have Graham.
Lovely.
Dorian and Sako. They're always together. Roshan. Dana. My favorite. This one's so cute. We have Jaka. I don't have everyone up here just because of the time, but Nicolas, these are the people that I saw most frequently on these meetings. Tron, thank you so much. So you'll each have a seal that's named after you. And Victor.
Awesome.
I'll stop sharing.
This one caught me by surprise. Very nice.
It'll take us a little while to figure that out and get in the data set, but we will. So thank you guys.
Super
Ahmet,
cool.
I don't know if you're still here. He might be teaching.
Yes. Thank you all. Like, it was really, you spent tons of time and we really appreciate it. And I believe that all the SEAL researchers will appreciate it also.
That's right. That was in my notes. Sorry. Yeah. I mean, there's no one who knows who knows more how hard this is than Ahmet and I, because we got as far as we did after about a year, 2 years maybe in. So thank you for jettisoning us a little bit closer, because now we can share things with SEAL researchers around the globe and other conservation biologists, hopefully, if it can be extended to other species. So what you've done is amazing. Absolutely amazing. Thank you.
I hope I speak for everyone when I say that it was a pleasure. For me, at least, it was. I really enjoyed the challenge. So from my side, I really enjoyed working on it. So our pleasure. But first of all, I really want to thank everyone for putting all the hard work into this project. I think this is one of the projects we've managed so far that came up with the best results, or at least as far as we got with the application, as well as with how well the recognition model works and the face detection model. So I'm also really proud of this project myself. Yeah, based on the results. So I hope you all are very proud of yourselves as well. I, of course, hope to see you all in future challenges again. And for the people who will still be continuing working with Krista and Ahmed for delivering the MVP of the SealNet, I really hope that you will do so with enjoyment as well. Big thank you to everyone. And yeah, I hope to see you again. So goodbye for now. Or yeah, no, I think I will see you in the upcoming week in Slack and everything. But I hope to also see you in future challenges. So, all right.
See you guys. Bye.
Have a fruitful day.
Thank you, everyone.
Again.
Bye.
Cheers.
Bye.
Cheers.
Bye.
Bye bye.
All right.